Exponential growth and decay are not always written in the form a times b to the power of t, but there are different forms, most of them typically something like this: a times 2 to the power of this small t divided by capital T. Or then if it is a decay, there is just a minus additionally here. Let us look at an example to understand how this works. We have a population of deer, P of t, in a region with a hunting ban, and that can be modeled using the function 1000 times 2 to the power of 0.2 t. And t means here the years measured since the ban was imposed. So 1a, let us rewrite this here in the form a times 2 to the power of small t divided by capital T. The capital T is this parameter. So we have P of t is 1000 times the 2 to the power of 0.2 t. This means we have now to get somehow this 0.2 into this form. Well, 0.2 is just 1/5, so we have 1000 times 2 to the power of 1/5 t. So we have 1000 times 2 to the power of t divided by 5. So our capital T is 5. Now we have it in this form here. What is the initial population and the population after 1, 5, and 10 years? Well, initial population P of 0. Let's use now this formula here. 1000 times 2 to the power of 0/5. 0/5 is 0, 2 to the power of 0 is 1, so we get the initial population is 1000, so that's again the A. What is the population after 1 year, for example? Well, 1000 times 2 to the power of 1/5, which means 1000 times the 5th root of 2, and we get approximately 1149. The population after 5 years, well, that's 1000 times 2 to the power of 5/5, which means 1000 times 2, so we get 2000. And the population after 10 years is 1000 times 2 to the power of 10/5, so 1000 times 2 to the power of 2, which means we get 4000. What is the meaning of the parameter a in the general formula up here? Well, we have seen before P of 0 in our example is just the 1000, so the a, we suspect that f of 0, or that a corresponds to the initial amount. So let's look at f of 0 in the general formula, and we get a times 2 to the power of small t is the 0 divided by whatever the capital T is, and we get a, because 0 divided by something is also 0, so 2 to the power of 0 is 1. We get a here, so a is the initial amount. What is the meaning of the parameter capital T? Well, in our example, we found that the capital T is 5, and what have we seen? The amount after 5 years is 2000, so double the original one, and after 10 years it's 4000, so the double of what it was 5 years ago. So we suspect that the capital T is this doubling time. So let us show that by looking at f of capital T. So we have a times 2 to the power of capital T divided by capital T. So we have 2 to the power of 1. So we get 2a. So what we found, T is the doubling time. As a last step, let us rewrite our function P of t here into our usual form a times b to the power of t. So we get P of t is 1000 times 2 to the power of t divided by 5. And we can write that now as 1000 times 2 to the power of 1/5 times t, which means we get 1000 times 2 to the power of 1/5, the whole thing to the power of 2. So this is 1000 times approximately 1.149 to the power of t, and we have rewritten the whole thing in the form a times b to the power of t. In example 2, we look at a diesel generator that is switched off and the current dies off according to this formula here in amperes, where time t is the time in seconds after the power is cut. So start by rewriting this formula in this form, try it on your own, and here comes the result. I of t is then just 24 times the 2, and now we can rewrite that as the minus 2.5. Let us write it as 1 divided by, sorry, minus here, 1 divided by 2.5 times t, and we'll realize 1 divided by 2.5, we get minus t divided by 0.4, 2 to the power of that. So what is the initial current? And that after 0.4 seconds, 0.8 seconds, and 1 second. So here again, the capital T that we found is 0.4. So the initial current is current after 0 seconds, 24 times 2 to the power of minus 0 divided by 0.4 by inserting the 0 here for the t here. So we get 2 to the power of 0 is 1, so we find 24 amperes. The initial the current after 0.4 seconds, 24 times 2 to the power of minus 0.4 divided by 0.4. So we have 2 to the power of minus 1. Well, 2 to the power of minus 1 is just a half, so we find it's 12. The current after 0.8 seconds, 24 times 2 to the power of minus 0.8 divided by 0.4, so 24 times 2 to the power of minus 2. 2 to the power of minus 2 is the same like 1/4, so we find that it is 6. And the current after 1 second, 24 times 2 to the power of minus 1 divided by 0.4. Well, that's 24 times 2 to the power of minus 2.5. And here we need our calculator, and we get approximately 4.24. What is the meaning of the parameter t here, the 0.4? Well, let's look at f of t. Sorry, in the specific case here, when for t equals 0.4, here we have looked at the current after 0.4 seconds. We found it's 12, so it's half of the 24. And after 0.8 seconds here, which means another 0.4 after the first 0.4 seconds, we get to 6, so half of that at 0.4 seconds. So we assume it is the half-life. So let us prove that. F of t in the general formula is just a times 2 to the power of minus capital T divided by capital T. So we get a times 2 to the power of minus 1, which means a half times a. So we have shown T is then the half-life. So here, when we have a minus, we have a decay. When we don't have the minus, we have growth, and the capital T is just the parameter. It describes the doubling or the half-life, doubling time or half-life. Let us rewrite our formula I of t in the form a times b to the power of t. So we have I of t is 24 times 2 to the power of minus t divided by 0.4. So we said that's the same like 24 times 2 to the power of minus 1 divided by 0.4 to the power of t, which is approximately 24 times 0.177 to the power of t. And sorry, this here should be small t, not capital T. To finish this section, let us look at the relationship between the two formulae y equals a times b to the power of t, so our standard form of the exponential growth and decay, and these other formulae a times 2 to the power of t divided by capital T, or a to the times 2 to the power of minus t divided by capital T. And we see here that our exponential growth factor b corresponds just to 2 to the power of 1 divided by capital T, or in the case of a decay, 2 to the power of minus 1 divided by capital T. Why is this the case? Well, we can just insert f of t into this formula. Let's say a times 2 to the power of minus t divided by capital T, this general formula for the exponential decay in the new form, and rewrite it as we did here. And now we get here that we can write it in this way here, which means our new b is this bracket, so 2 to the power of minus 1 divided by t. And obviously, if I don't have the minus here, I'll get it without the minus as here. As I said just before, in this form here, what do I get? 2 to the power of 1 divided by t. Without the minus, I'll get something larger than 1. I'll get a root or something of 2, which is always larger than 1. So my b is larger than 1, so that explains why this is exponential growth. If I have a minus here, 2 to the power of minus t divided by t, well, I'll get 1 divided by this 2 divided by t divided to the power of t divided by t. So since this here we said before it would be larger than 1, now 1 divided by it, I get something between 0 and 1. So that's the reason why this is exponential decay.